Right, it looks like it's time to start section 2.5 in the book, and we're going to take some of the functions we've been working with and transform them, or just move them around in the XY plane. We've got a list of objectives over here, and I believe I have chopped this section up into 3 days worth of classwork and notes. Of course, today we're going to do the first one, recognize the graphs of the common functions. We'll look at vertical shifts up and down and horizontal shifts left and right. And I believe we'll get to the reflections in the next video or the next day in class. So what do we mean about transformations? Have you seen the movie Terminator 2, The Mask, or The Matrix? These were among the first films to use spectacular effects in which characters or objects having one shape are transformed in a very fluid fashion to a different shape. The name of such a transformation is a morphing. The effect allows a real actor to be seamlessly transformed into a computer-generated animation. The animation can be made to perform impossible feats before it's morphed back to a conveniently filmed image. So like a transformed movie image, the graph of one function can be turned into a graph of a different function. To do this, we need to rely on a function's equation. Knowing that a graph is a transformation of a more familiar graph makes the graphing easier. That guy looks familiar, doesn't he? All right. Here are a quick little table of the common algebra graphs. The first one's a horizontal line. That's just in the form of y equals some number. There's no slope, so we find our y-intercept, draw a horizontal line through it. The basic identity function, or the basic linear function, is just y equals x. Whatever your x coordinate is also your y coordinate. So 1, 1, 2, 2, 3, 3, and so on. You know, that is a line. It has the y-intercept of the origin, slope of 1. Our absolute value function is in a V shape. Remember, absolute value makes things positive, so this graph never goes below the y-axis. And you can see that here in the range. The range is just 0 to infinity, while the domain is all real numbers. And backing up, domain and range on the basic line function is all real numbers. Down on the lower left, now we're into, again, let me stress that for our linear function, it is x to the first power. Once we get up to x to the second power, we've bent our line into a parabola. Domain, all real numbers. Range is all the positives. We decrease until we hit the origin, and then we increase after that. The square root function. Remember, you only put positive numbers under an even index, and only positive numbers come out. So that there restricts us to the first quadrant. Our domain is all the positive numbers, 0 to infinity. Range is also just the positive numbers, 0 to infinity. The cubic function. I like to say, you know, if that was squared, we would have an upward opening parabola. When you make, and when we have our upward opening parabola, if you square a positive number, you get a positive output. When you square a negative number, you also get a positive output. And that's what gives the parabola its shape. And for our cubic function, that also holds true in the first quadrant. If we cube positive 1, we get positive 1. If we cube positive 2, we'd be way about up here, positive 8. But when we plug a negative number into the cube function, it will come out as a negative output. So that's sort of taken this part of the parabola in the second quadrant and bending it down into the third quadrant. So now it goes up to the right and down to the left. Oops, I didn't mean to do that. Domain, all real numbers. Range, all real numbers. And notice this function is always increasing. If we start here at negative infinity and work our way up, this is a positive slope. We're increasing, increasing, increasing. We do start to flatten off, and if you take calculus in a couple years, you will see there is one point in here where there actually is a horizontal tangent line, but then you go right back to increasing. The cube root function is very similar to the square root function, but we can put negatives under odd indexed radicals. So we could take the cube root of -1 is -1, and that gives us a reflection down here into the third quadrant, very similar to what we have in the first quadrant, again for that cubic function. So if you know these basic shapes, finding a function transformation is pretty simple. So we'll start with the easiest of them, and that's a vertical shift, a shift up or down. Let's look at 3 graphs whose shapes are the same. The figure here on the bottom of this slide shows the graphs. The black graph in the middle is the standard function, f of x equals x squared. That's our basic parabola going through the origin. Now look at the blue graph above it. The equation of this graph is x squared plus 2. And then we have this other purple graph, and we see that is x squared minus 3. Well, if I can trace over this parabola pretty nice. So I just traced over in black the basic parabola x squared. If we put a plus 2 at the end of it, that takes that parabola and just shifts it up 2 units. For the x squared minus 3, we're back to our starting position, the basic y equals x squared. If we move that down 3 units, now we have x squared minus 3. So a lot like the y-intercept of y equals mx plus b. You know that for a parabola will also be our y-intercept. If we have a shift up or down, it'll be a number added or subtracted after the x squared. So the official book definition here, let f be a function and c be some positive real number. The graph of y equals f of x plus c is the original graph, f of x shifted c units vertically upward. And on the other hand, if c is negative, then it would be a shift vertically down, whatever units c represents. All right, let's try it out. First, we need to know the basic shape of our absolute value of x function. And if you don't memorize it, you can always recreate it. The absolute value of 1 is 1, the absolute value of 2 is 2, 3 is 3, and so on. And then when we go to our negative domain numbers, the absolute value of negative 1 is positive 1. The absolute value of negative 2 is positive 2. So we get that distinctive V shape. And we do go through the origin. So there's our basic graph, the absolute value of x. Now here they want us to find the absolute value of x minus 4. So imagine, I'll do this in red here, each of these points gets shifted down 4 units. Our new y-intercept is now at negative 4. And if you want to think about this as slope, from that point we had a positive slope of 1 to the right and a slope of negative 1 to the left. Or just think about each and every one of these points has been shifted down 4 units. So our graph of our vertically shifted function is going to look like this. Again, if I just took my original, f of x equals the absolute value of x, and move it down 4 units, there's my shifted graph, the absolute value of x minus 4. And notice that negative 4 was outside of the absolute value bars. We do the absolute value first, and then we subtract the 4. That's what shifted us down. Now, a horizontal shift is left or right. We return to the graph of the parabola, f of x is x squared. In the figure below, the graph of function f is in the middle of the 3 graphs. By contrast to the vertical shift situation, this time the graphs are shifted left or right. So if we have f of x equals x squared, again, that's the one in the middle. Now, instead of putting a plus or minus a number outside of the squaring function, a horizontal shift will actually be inside the thing that we're squaring. So we're going to have x plus or minus some number. That number is our shift left or right. And the way I like to think about this is it's sort of counterintuitive. I'm going to trace over my basic parent function here in red. Now, one of the graphs is x minus 3. Notice the 3 is in the parentheses with the x minus 3 quantity squared. Now you'd think since that is a minus 3, you would be a shift to the left on the x-axis where the negative numbers are. But again, this is counterintuitive. Whatever that sign is, you want to go in the opposite direction. So x minus 3 quantity squared means I'm going to shift to the positive direction 3 units. So I'd pick up this parabola and move it 1, 2, 3. Now it's right on top of that blue parabola, which is x minus 3 quantity squared. On the other hand, here's x plus 2 quantity squared. Again, the plus 2 tells us our shift, and it is 2 units, but now we're going to the left. So in this case, again, sort of counterintuitive. A plus in there, a positive shift would be to the left, or a negative shift would be to the right. So let f be a function, c is some positive real number. The graph of y equals f of. Now we're messing with that x number before we actually perform the operation on it, like the squaring function in the last example. So if that is a plus, it is a shift to the left c number of units, whatever number c is. F of quantity x minus c is the f of x graph shifted to the right, c units. And again, if somebody has a question, here's a great one. Using my intuition, it seems that f of quantity x plus c should be a shift to the right, and f of x minus c should be a shift to the left. Is my intuition on target when it comes to these horizontal shifts? No. On a number line, if x represents the number and c is positive, then x plus c is a shift c units to the right, and x minus c is a lies c units to the left of x. This orientation does not apply to the horizontal shift. F of quantity x plus c causes a shift of c units to the left, and f of x minus c causes a shift of c units to the right. So let's try this one out. Again, here is a different parent function, the square root of x. If you don't have this one memorized, again, it's easy to recreate quite simply. The square root of 0 is 0. The square root of 1 is 1. The next perfect square here would be 4, and the square root of 4 would be 2. So here we sort of have a parabola laid on its side, only in the first quadrant. So there is f of the square root of x. Now we want to find the square root of x plus 5. And again, the 5 is under the square root sign. If we had the square root of x plus 5, if the 5 isn't under the radical with the x, that would just tell us we're shifting this graph up 5 units. But that's not what they're asking. You know, the 5 is under the radical, so we're messing with the x, and then we're square rooting. So that means it's a shift left or right. And again, because that's a plus, I want to think opposite direction. I want to head toward the negative side. So where this graph started at the origin on the x-axis, this graph will start at negative 5 on the x-axis. And then we'll go over 1 and up 1, so over to negative 4 and up 1. And let's see, from that point we could go up 1 and over 3, up 1 over 3. So the graph is going to look like this. Again, it's sort of like we just picked up this graph and moved it 5 units left. If, on the other hand, under that radical, let's say it was the square root of x minus 2, I would just pick up my basic graph, the parent graph, and move it 2 units to the right. Ooh, it looks like we have another great question down there. Let's see what this is all about. Get there a little bigger. Come on. There it is. So what's the difference between f of x plus c and f of quantity x plus c? If the c is outside of the operation, it's a shift vertically up or down. If you're doing f of quantity x plus c, if you're messing with the x value before you're performing some operation like squaring or square rooting it, then that's going to be a shift left or right. All right, now let's do some combinations of shifts. We're going to graph h of x is x plus 1 quantity squared minus 3. Well, let's think about it in incremental steps. First, our parent function. 1 squared is 1, 2 squared is 4, negative 1 and negative 2 also square to those values. So here is our parent function, or our basic function. Now we're going to start working sort of inside out on that. So we're going to work with the x in here and do the x plus 1 quantity squared. Well, since we're messing with the x before we square it, that's a shift left or right. That's a plus 1, so that means we have been shifted to the left 1 unit. Now we're touching the x-axis at the origin, or I mean not at the origin, but now shifted left 1 unit to negative 1. And then we're going to have our first 2 points here and here. And then from those points, I guess we could go up 3 and over 1. And from here up 3 and over 1. So I've taken every point on the parent graph, and every one of those points got shifted to the left 1 unit. Now our parabola looks like this. Now from that parabola, we're going to do a downward shift of 3 units. So we have our minus 3 at the end. That means everything goes down 3. So this point that was at negative 1, 0 on the x-axis is now down here at negative 3. This point that was right on the y-axis goes down 3 units also. So it's going to be here at negative 2 on the y-axis. We'll have a point here. This point that was at positive 4 got knocked down 3 units. So now it's going to put it right here and right here. We could just take every y value and subtract a 3 from it. And here's, ooh, that wasn't very good, but you get the idea. Here's our final graph. F of, or h of, x is x plus 1 quantity squared minus 3. We took our parent graph, moved it left 1 unit, down 3. All right, that's enough talking for me. Try checkpoint one. We're just shifting the absolute value function. Here we're shifting a radical function. And the last one is we're doing a couple things. So try to graph those. Pause the video, graph them, and then fire it back up and see if you got them. Okay, the first one, our parent function is the absolute value of x. That starts at the origin, slope of -1 to the left, slope of +1 to the right. Now we're doing the absolute value of x plus 3. So everything got shifted up 3 units. So the point that was at the origin is now at 3 on the y-axis. And from there, it's easy enough to draw our lines diagonally through the graph paper. So up to the left and up to the right. There's our shifted function, g of x. Checkpoint 2, square root of x function. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. We'll almost get to 9, so the square root of 9, that would have about it right up there at 3. And here is our parent function. And then from there, notice now we are still under the radical quantity x minus 4. So we are going to shift 4 units left to right, and because that's a minus, we want to shift to the plus side. So let's see here. This point got shifted over 4 units. This one got shifted over 4, and you get the idea. So we're here at 4. We got another one here. And I guess from that point, we could go up 1 over 3. Takes us to 8, 2. And there's our shifted square root function. Last one, we do the old double whammy. First, we graph the parent function, square root of x. So there's our square root of x function. And the first thing we want to do is see if there's anything we're going to work under the radical, and there is, x minus 1 under the radical. So that's a shift 1 unit to the right. So now we're going to start at 1 instead of the origin, and then we'll go up 1 over 1, and then up 1 over 3 to get a couple more. Ooh, I went a little too far on that one, over 3. So there's our square root function shifted 1 unit to the right. That would be radical x minus 1. And now we're going to take that graph and give it a vertical shift down 2 units. So every point gets knocked down 2 units. We were at 1 on the x-axis, now we're down here. We were at 2, 1, so instead of going over 2, 1, we go down 2 units from there. And then our last point, it will be, since everything got shifted down 2 units, this point that did have a y height of 2 got knocked down, and it's right on the x-axis at 5. That's a pretty nice point to know, being that it's an x-intercept. So our graph starts here and goes up and over. There we go. All right, there's the assignment for tonight, page 283. And if I remember right, I might have some graph paper to pass out for you. Of course, but you're not in class watching this, you're at home. So do the best you can with the graphs if you don't have graph paper.